Welcome back to Electro-Knowledge, the channel where we make complex circuits make sense.
Electro-Knowledge. Power up your concepts.
Today we're diving into something that looks kind of like magic, but is actually just really smart engineering: phasor diagrams. We're turning those crazy AC waves into something a bit more manageable. Let's get into it.
Right, so it all boils down to this one question. How on earth do you take a constantly changing sine wave and represent it with just a simple spinning arrow? It feels a little like cheating, doesn't it? Like you're turning this complex flowing wave into a straightforward little pointer. So what's the secret? Okay, so here's the big idea. Trying to analyze an AC circuit by just looking at its constantly fluctuating voltage and current is, well, it's a nightmare. Imagine trying to describe a wild roller coaster by just listing its height at every single millisecond. You'd have a mountain of data, but you'd totally miss the big picture. And that's exactly where the phasor comes in. The name might sound like something from a sci-fi movie, but it's really an engineer's ultimate shortcut. It's a special vector that cleverly packs two crucial pieces of information about a wave into one little package: its peak height, which we call amplitude, and its starting point in the cycle, which we call its phase. It's basically a GPS coordinate for a wave. Okay, so you're calling it a phasor vector. But is it just a fancy arrow? What really makes it so special? That's the perfect question. It is so much more than just a static arrow. Think about a Ferris wheel at night, all lit up and spinning. A phasor diagram is like taking one single photo of that wheel, right at the instant the ride begins. That one snapshot tells you where every single card is and how far it is from the center. We use phasors to take that same snapshot of voltage and current at one specific moment. And this right here is the aha moment. This is where it all clicks together. As that phasor on the left spins around, imagine a light casting its shadow onto the wall to the right. That shadow dances up and down, and in doing so, it perfectly traces out that classic sine wave. When the phasor points up, the shadow is at its peak. When it's horizontal, the shadow is at zero. It's this beautiful direct link between simple rotation and a complex wave.
So we should always imagine these arrows as being in constant motion? Always. Every single phasor is spinning at a steady speed, kind of like a record on a turntable. And just so every engineer is on the same page, the rule is they always spin counterclockwise. One complete 360-degree rotation of that phasor gives you one full up and down cycle of the sine wave.
Okay, so that's the theory. But theory is one thing. Let's see how this actually works with some real circuit components. We're going to start with the simplest component of all, the humble resistor. You know, with a resistor, life is easy. Good old Ohm's law runs the show, and there are no weird time delays or anything funky going on. This means the voltage and current are totally in sync, like two runners who hit their peaks at the exact same time and cross the zero line at the exact same time. We call this being in phase.
Okay, so if they're in phase, does that mean their arrows on the phasor diagram are identical? Like the same length? That's a really good question and a common point of confusion. Not necessarily. On the diagram, they point in the exact same direction, like two cars driving in the same lane. But one car, the voltage, might be a huge truck, and the other car, the current, might be a little sports car. Their lengths can be different based on the resistance, but what matters is that they are always pointing in the exact same direction.
All right, so we've handled the resistor. That was kind of the tutorial level. Now, let's bring in the other key players that make AC circuits so interesting: inductors and capacitors. And to remember how these two behave, engineers have a secret handshake, a mnemonic that has saved countless students on exams. You have to remember this phrase: ELI the ICE man. Trust me, this little saying is pure gold. So let's break down the first half, ELI. E stands for voltage, L is for the inductor, and I is for current. So ELI tells us that for an inductor, L, the voltage, E, comes before the current, I. You can think of an inductor like a really heavy, rusty gear. You have to apply a force, the voltage, first to get it to start turning. That's the current. So what does it actually mean for the voltage to lead on the phasor diagram? It means there's a specific gap between them, exactly 90 degrees. So if you picture the current phasor pointing straight to the right, the voltage phasor is already a quarter turn ahead, pointing straight up. With an inductor, the current is always lagging behind, playing catch-up. Now, let's look at the other half of our friendly mnemonic, ICE. That stands for current, capacitor, and voltage. This tells us that for a capacitor, C, the current, I, comes before the voltage, E. And this makes total sense. Think of a capacitor as an empty bucket. You have to have a flow of water, the current, first, before any water level, the voltage, can build up inside. So for a capacitor, it's the complete opposite of an inductor. Using that same car analogy, if the voltage phasor is pointing to the right, the current phasor is the one that's 90 degrees ahead, pointing straight up. In the world of capacitors, the current always gets the head start. Okay, so we've got the rules for resistors, inductors, and capacitors down, but that brings us to the most important question of all. So what? Why bother with all this? Let's talk about why this isn't just a neat little trick, but an absolutely critical tool for every single electrical engineer.
Exactly. I'm following along, but why? Why go through all the trouble of turning these waves into arrows in the first place? Why can't we just stick with the sine waves we started with?
And this is the magic trick. This is the entire reason we do it. If you try to add two sine waves together, you're looking at a nightmare of trigonometry. It's complicated and messy. But when you convert them to phasors, adding them is as simple as adding two arrows. You just put them tip to tail. It literally transforms a really hard calculus problem into a simple geometry puzzle.
And engineers use that super simple puzzle to figure out all the important stuff. They can calculate something called impedance, which is just the total opposition to current in the circuit. They can see at a glance if voltage or current is leading or lagging. And they can calculate the power factor, which basically tells you how efficiently the circuit is using electricity.
So, to put it simply, phasors are an amazing invention. They take the messy, chaotic dance of AC waves and freeze them into a simple, static snapshot that makes all the math ridiculously easier. It's the ultimate tool for taming the beast that is AC circuit analysis. So here's a final thought for you. The next time you see the power lines running down your street, don't just see wires. Picture those invisible waves of voltage and current flowing through them. And know that engineers are using these simple little arrows, these phasor diagrams, to make sure that all that power flows perfectly, all the way to your home. It's a whole new way of seeing the invisible world around us. We hope this explainer helped you get a handle on the awesome power of phasor diagrams. If you learned something new today, do us a huge favor. Hit that like button, share this with anyone else learning circuits, and of course subscribe to Electro Knowledge for more. Thanks so much for watching.
Thanks for watching. Like, share, and subscribe to Electro Knowledge for more electrical concepts.